As I promised at the end of the first section, we're going to come back to page 7 at the end to do the problems that we set up previously. So at this point, you need to have your notes open to page 7, which should be complete. We're going to complete the problems we set up at the end of section 12.1. You'll be expected to complete them during the presentation, so you will need your usual equipment, meaning your periodic table, calculator, scratch paper. At this point, we've gone through several problems where we used the 3 steps of stoichiometry. All stoichiometry problems follow the same steps. These steps can be found on the back of your periodic table on the bottom right-hand side. The first step is to convert what you have to moles using the correct conversion factor. For example, if you were given grams, you would take the grams times 1 mole of what you have divided by the molar mass. If you were given liters, you would do whatever you were given times 1 mole over 22.4 liters. Whatever of the 4 types of conversions that we learned in chapter 10. Once you have converted what you have to moles, then you're going to multiply by the mole ratio from the balanced equation to get the moles of what you want. This step 2 is one that's done in every stoichiometric problem. There's no way around it. Steps 1 and 3, if I was given moles, I wouldn't have to do step 1. If I wanted moles, I wouldn't have to do step 3, which is taking the answer from step 2 and multiplying it by a new conversion factor that will give us the units that we want. So I have the steps listed here. H times 1 mole over whatever the units are for H, and then you multiply by the mole ratio of what you want over what you have, and the last step you multiply by whatever unit you want per mole. So let's jump right into this. Here are the 5 equations. I'm not going to spend a lot of time on these because we've already gone over these. These 5 equations are going to be used with the problems. Now, we set up back then that we have 1.25 kilograms of potassium oxide, and we want to know how many kilograms of copper would be produced when it decomposes. So the mole ratio that we set up was 2 moles of copper over 2 moles of copper 2 oxide, which comes from the balanced equation. So that's going to be our step 2. But the first thing we have to do is we have to take our 1.25 kilograms of copper 2 oxide, and we want to convert it to moles. But since we have kilograms, we're going to use kilomoles, just so everything is consistent. You can do that in chemistry. So the first step is I need to get rid of my kilograms of copper 2 oxide, so I need the molar mass. What is the molar mass of copper 2 oxide? To 1 decimal place. Yes, it is 79.5 kilograms of copper 2 oxide per mole. So on the numerator, I put 1 kilomole. On the denominator, I put 79.5 kilograms to cancel out my 1.25 kilograms. So my next step is I'm going to use the mole ratio, which we have. We have 2 moles of copper 2 oxide and 2 moles of copper. So we already did this step back in section 1. The third step is I need kilograms of copper, so I look up the molar mass for copper, and that is 1 kilomole of copper is in every 63.5 kilograms of copper. Now, I want to do my math, and when we do our stoichiometric math, once we have all our units to knock them down, is we're going to multiply across the top and divide across the bottom. So do that now. When I multiply 1.25 times 1 times 2 times 63.5, then I'm going to divide it by 79.5, then I'm going to divide it by 2, and then I'm going to divide it by 1. And when I do that, I get 0.998 kilograms of copper. The second problem. This time we have 22 grams of hydrogen, and we want grams of ammonia. The balanced equation is there, so my first step is to convert from grams of hydrogen to moles of hydrogen, so I need the molar mass of H2. The molar mass of H2 is 2.0 grams because there's two H's and H is 1.0. On the top, I'm going to put 1 mole. That way I can go from grams to moles. My second step, I'm going to use my mole ratio from what I have up there. I'm going to put the 3 moles of hydrogen on the bottom and 2 moles of ammonia on the top to get rid of my moles of hydrogen from step 1. And my last step is I want grams of ammonia, so I need the molar mass of ammonia. I'm going to put 1 mole on the bottom, and the molar mass of ammonia is 17.0 grams. So now I'm going to do my math. But before we do this one, I want you to cross out your units as you go. And as you cross them out, you'll see that the grams of hydrogen cancel, the moles of hydrogen cancel, the moles of ammonia cancel. You're left with grams of ammonia. But what will reduce is the 2 in 2 moles of ammonia with the 2 in 2.0 grams of H2. So 2 over 2 is 1. So I'm just going to cross those off so I don't have to do as much math. So my math now is 22.0 times 17 divided by 3. And to 3 significant digits, my answer is 125 grams of ammonia. Number 3, this time we have 17.54 grams of sodium hydroxide. We want to convert that to grams of hydrogen using the balanced equation. So my first step is I'm going to get rid of the grams of sodium hydroxide using the molar mass. And we have to calculate the molar mass with 1 sodium, 1 oxygen, 1 hydrogen. To 1 decimal place, it is 40.0 grams. Well, if I get rid of the grams, I have to put 1 mole on the top because there's 40.0 grams of sodium hydroxide in a mole of sodium hydroxide. So now I have moles of sodium hydroxide. I'm going to use my mole ratio. I'm going to have 2 moles of sodium hydroxide in my denominator, so it cancels the 1 mole of sodium hydroxide in the previous step. I'm then going to put my 1 mole of hydrogen from my balanced equation in my numerator. But I don't want moles, I want grams. So my last step is I have to calculate the molar mass. So I'm going to put 1 mole of H2 on the bottom, and the molar mass for H2, as we did before, is 2.0 grams. So now, once again, I'm going to do my math. But before I do my math, I'm going to cross out my 2.0 and my 2 from 2 moles of sodium hydroxide. So now my math is simply 17.54 divided by 40.0. When I do that, I get a grand total of 0.4385 grams of hydrogen. Since I started with 4 significant digits, I must end with 4 significant digits. Problem 4. This time I have 25.0 grams of acetic acid. I want to solve for grams of carbon dioxide, and my mole ratio is 2 moles of carbon dioxide over 1 mole of acetic acid from the balanced equation. So I'm going to start as always. I'm going to put what I have out front. To cancel out the grams of acetic acid, I'm going to put the molar mass on the bottom. And the molar mass for acetic acid is 60.0 grams. As always, my first step, I'm going to put 1 mole of acetic acid on the top because that's equal to 60.0 grams. I'm now going to use my mole ratio, 1 mole of acetic acid on the bottom to cancel the previous moles, and 2 moles of carbon dioxide to get to what we want. But I don't want moles, I want grams, so once again, I'm going to put 1 mole on the bottom of the last step and the molar mass on the top. And the molar mass for carbon dioxide is 44.0 grams. Now I look at my math, I don't see anything simple, so I'm just going to do the regular math. Multiply across the top, divide across the bottom. And when you do that, you get 36.7 grams of carbon dioxide. Once again, I start with 3 significant digits, I end with 3 significant digits. Last but not least, number 5. This time, we are forming 20.0 grams of iron 3 sulfide. We want to know how much iron in grams we needed to get this. We have our mole ratio of 2 moles of iron over 1 mole of Fe2S3 from the balanced equation. I'm going to start by putting my 20 grams out front, and as always, we're going to divide by the molar mass. You know the drill. Yes, the molar mass is 207.9 grams. Since molar mass is on the bottom, 1 mole goes on the top. Second, we use our mole ratio from the balanced equation. We want iron, so we put the 2 moles on the top, and we put 1 mole of Fe2S3, not 1 mole gram, just 1 mole. Last step, I want grams, so I put 1 mole of iron on the bottom, 55.8 grams on the top, and I do the math and I get 10.7 grams.